So in 1991, the population of a town was a perfect square. 10 years later, after an increase of 100, oh wait. Okay. In 1991, the population of a town was a perfect square. 10 years later, after an increase of 150 people, the population was 9 more than a perfect square. Now in 2011, with an increase of another 150 people, the population is once again a perfect square. Which of the following is closest to the percent growth of the town's population during this 20-year period? Okay. So how do we approach this? Well, we first say that in 1991, the population was k squared for some integer k. And then 10 years later, the population, whatever 1991 plus 10 is, 2001, the years don't actually really matter. Yeah, in 2001, the population was k squared plus 150. And then in 2011, the population is k squared plus 300. And now we want to know the percent growth of the town's population during this 20-year period. And the percent growth will be 300 over k squared. The population grew by 300, and the original population is k squared. So we want to find 300 over k squared. But oh no, we don't know what k is. So we have to utilize the conditions that we got about squares. So firstly, we have that after an increase of 150 people, the population was 9 more than a perfect square. That means that k squared plus 141 is a square. And we also have that in 2011, the population was a square. So that means that k squared plus 300 is a square. So we have these two conditions which we want to utilize. And so since they're squares, we can write a squared equals this and b squared equals this. So now the usual thing you do when you have two squares which differ by some amount is you take the difference. So you get that a squared minus k squared equals 141, and b squared minus k squared equals 300. And the reason why we do this is because we can factor this as a minus k times a plus k and b minus k times b plus k. Okay. And so now the top condition is quite a bit stronger because there's not a whole lot of ways to assign integers a and k so that such that a minus k and a plus k multiply to 141. And one way to do it would be for them to sum to 141 and the difference to be 1. That dies if you run through it. In that case, you get that k, like a equals 71, and a equals 71, k equals 70 is one possible solution, but then this dies when you try to substitute that into the equation with b. And then the other choice is when a minus k equals 3 and a plus k equals 47, which means that a equals 25 and k equals 22. And then in this case, when we plug this back in, we can actually get a value of b, and b can be hit. B works. There's a value of b that works here, which is 28. The way I did it when I was doing this problem was that like the increase from 22 squared to 25 squared is 141. So then in order to get a difference of 100, you need like double 141. So it should be around 28 squared. And then 28 squared works because 28 squared minus 22 squared equals the difference, 6 times the product times the sum, 50, so 6 times 50. And so yeah, we've found a solution and k equals 22 is the answer. And so we want to find 300 over 22 squared. That's the answer. And then you just do long division. This is like 75 over 121. And then 75 divided by 121 is equal to approximately 62%. Okay.